Let's go over the things I learned 2 weeks ago and some things I did today for competitive programming and just the introduction of that in C++. So in the front, we have just basic kind of notes that I asked Gemini to summarize that I took first, and then it kind of rewrote it for me in a much neater sense. So then first we have kind of the header that we use a lot quite often is include bits std c++ .h. I guess it's a very nice shortcut because we kind of don't have to worry about which libraries we need to import, right? Like the IOStream, vector, algorithm, I don't know, like math, like it's basically everything is just incorporated into this um, one line. And something else that is really nice to use is using namespace std, which saves a lot of typing std and then the two colons, right? Because for C and C out vector, these use it quite a lot. So that's just two little shortcuts that's really useful. And then to compile things, it's nice to have G++ and then the CPP file um, converted to object file called this name test. And then we have this executable named test. And then we can specify it further by talking about which version of C++ we use. And then this command tells us that we want to optimize for speed. And then WALL just means all warnings. So we can perhaps get some kind of potential bugs before we run the code. Some other kind of things that are pretty neat is iOS Sync with Studio Zero, which basically just disables the synchronization between C and C out, scanf, printf streams. So then that makes it faster. And tie 0 kind of unties C from C out. So it just kind of um, prevents the flushing. So basically you don't have redundant flushing. So that makes it faster. And it's the same kind of rationale for why the slash n is better than endl is because endl flushes the output buffer, whereas slash n doesn't. So if we're in a loop and we're going to constantly do endl, then we're going to have a massive kind of time operation on that. And some other kind of tricks for kind of making things easier is like, for instance, if you have input that's very long, you can just kind of create a file and then you can just do FRE open and then the file name and the R standing for read, STD. And so basically that can prevent, you can kind of skip the keyboard and like the typing. And then if you want to output, you can save it and write to the output txt. But obviously, if you're submitting to online judge, you want to definitely remove these two things before actually submitting the code. And then some other kind of logistics to know about things is that our int is 32-bit. This is basically around 2 times 10 to the 9. And then our long long is 2 times that. And then anytime we see 10 to the 9, anything bigger than 10 to the 9, it's definitely good to switch to long long because long long can store up to 9 times 10 to the 18. And then we kind of want to just watch out for long long because at the end it just has this kind of suffix ll, which tells that it's a long long, not a int. And then some classics kind of trap to kind of avoid with long long is making sure that you first convert the thing on the right hand side before you do the equality because here we're going to be exceeding the limit because a is an int times int is an int. So then int is stored in a long long which exceeds the limit and hence we have a random negative number which becomes garbage value. So yeah, it's important to have such a bracket before doing the thing. Yeah. So other than that, most of the time C in and C out should be good. But sometimes it's good to like if you were to print in certain formats that you want, such as alignment, then printf would be the better option because it's easier to use with this percentage syntax. Some other things, kind of good things, is to take advantage of type def or also called using. So you kind of get to use the macros, define your own macros. So then what we can do is something like type def long long ll, which basically means anytime we type ll, it just treats it as if we type long long. So when we're doing typing the code, it's much easier to type ll than long long. So one line can simplify a lot of code. On top of that, for instance, we have data structures that are pretty long, like vector int or pair int. So we can just call that and shorten it with the type def, and then we can just use vi and pi, right? So that's pretty nice. Yeah, basically in modern C++, we kind of use the using syntax rather than the type def because it's nicer. It makes more sense. And the macros technically just basically is just like a nice way for humans to read the code and write the code, and then the machine just replaces it afterwards. Like if we were to say define f first, so then we can just access it, define s second. So we can just access that. Basically, you can just basically write the thing to be a long kind of statement into a very short, your defined version of it. But it's essentially doing the same thing. So it's just nicer for the person to do. And you can actually do it for even for stuff like for loops. For instance, you have this long for loop. You can just replace it by this. Technically, I'm not in favor of doing this because I think the for loops make me realize like the time complexity of my algorithm is easier to analyze. And this way of writing rep kind of misses that. Or if I have a, let's say, nested for loop, then it's kind of hard for me to kind of do it that way. Whereas writing the for loop is just more explicit for me. So I think I like to write it out this way. But it's definitely a nice thing to know that there are such a thing. You can do certain things like this. And yeah, that basically there's the speed and it avoids typos because it's kind of annoying to do like those things. So yeah, but it's my personal preference to keep it. I guess this doesn't have much things, yeah. Um, and zero index is basically creating that for zero. I think, yeah, that's pretty straightforward. It's just a personal preference. I don't really like it. But yeah, it's definitely something nice to know and could implement in the future. And then next we move into kind of talking about generating kind of subsets because we're kind of interested in that. So the typical way, like the more intuitive way, is kind of this binary choice and doing this recursive backtracking approach, where what we do is what would happen if I include it and what would happen if I don't, right? So then I just kind of break it down into these two cases. So I first define my vector of a int called subset, then I define my function called search, and I take in a parameter called k. So I just check if we're done our base case, which is if k is equal to n plus 1, so we're reaching the end, so we just process it. Otherwise, we're going to just do kind of subset dot push back k. So we're just going to push it into the thing, and then we're going to try calling the search with that thing inside, right? And now we're going to backtrack and say, okay, we're going back and we're taking this out. And now if we don't include it in that set, we're going to try searching that. So the idea is that we just do include, see what happens, backtrack, don't include, see what happens. And then we just get all the cases. But this is not a pretty good approach because it's kind of slow, right? Because you have to go through and you have to kind of remember what you have and everything. It's just not a good approach. So a better way to do that is kind of through the iterative bit mask, which kind of um, does it more explicitly, I'd say. Like if we're trying to generate 2 to the n subsets, we can just map it out directly. So what we have is we just have binary numbers from 0 to 2 to the n minus 1. So then we can just represent 0 if it's not in, 1 if it's in. So then we can just have that many elements and each one just represent. It's like a switch that tells me if it's in or out. So then what I can do with the code is I can just first I mean, this is just a library, and that I have my function called generate power set, and that I input the basically the vector inside that. Then I define my n to be the size of that. So that I'm just gonna go through the list, and then I'm gonna go see what I have, right? So I'm gonna loop from 0 to 2 to the n minus 1. So I go through every element of that. And then I'm going to basically, this is just for the formatting of the brackets so that the subsets look nice. But the core logic is in this for loop. Basically, what I do is for each of the n bits, I go through from j to equal 0, and then j smaller than or equal to n, j plus plus, I'm going through it. Then I'm going to check, okay, if my jth bit of the integer I is set to 1, then I'm going to output that. Otherwise, I'm not going to do anything. And then I can get what I need. So I think what comes down to it is that because we think about it, like, let's think if we have something that was mapped out explicitly using this, and each one was just a toggle 0 or 1, and we're just going to use the for loop that goes through this list. It's very, very straightforward, right? Like, I mean, not a list, but just a vector. Like, the idea is still the same. It's very simple. Whereas, if it was the thing that was the backtracking, then it would have been more difficult. But I'd say overall, in terms of time complexity, because you have to go through each operation, yeah, like your time complexity would be the same. But I say this method is much simpler to kind of implement and know. And then the second part that I was talking about is permutation, because like we were just talking about generating subsets. So now we're going to talk about generating permutation. So generating permutation is also broken down into two ways. Um, so we have first the method A, which is the recursive backtracking. So it's the same idea from earlier. Basically, you just try to see if you um, kind of just put it in or don't, and then you just pick from the remaining things whether you have it or not. So we have our vector called permutation. We have our bool chosen. So we just keep track whether if it's chosen or not. So we have our search. If we have picked everything, and which basically means our size of this is in, then we're just done. Otherwise, we would just go through from 1 to n. If it's already chosen, then we just skip it. If it's not chosen, then we can first try choosing it, and then we're going to push it back and we're going to search it. Otherwise, we're just going to choose not to choose it for now, and then we're going to kind of make sure we pop out of it, right? So I think this is just basically the idea that the same idea. We're going to try it, and then we're going to go back. That's the same idea. And then I'd say a nicer approach for this is definitely just using what C++ library has to offer. The next permutation, just taking advantage of this pre-made thing. So what you can do is you can just write basically first populate, which is already assumed that was done. So what you can do is the do while loop. So you have this next permutation, which modifies the array in place to the next um lexicographically greater permutation. So you do permutation dot begin, permutation dot end, and that is sorted in ascending order. So we're just gonna do this. So it's pretty nice that we can just use this something called next permutation. And then next we move into kind of more bit things, like bit operations. I'd say I made a better thing that was kind of talked about later on, but I think I'm just gonna go briefly over this before I go into my own notes. So first we have these. Basically, this is just a left shift. The idea behind this is that we can just treat it as if we were to have, let's say, a number like this. Let's say 100 in binary. Then what it does is it just adds an extra zero at the end of the thing. That's what left shift does. And for right shift, it does the opposite, except it moves, let's say, if it was this, if it shifts right, then it just takes this out. Right shift does that. And if it was 1 at that place, then 1 would be eliminated. So essentially, left shift can be thought of as multiplying by 2, and then right shift can be thought of as dividing by 2 and rounding down. And then there are just several kind of bitwise operators. Usually, and what we use with and is to read something. If we're going to try to set something, we usually use the or operator. To clear something, we usually use a combination of and not to kind of cancel things out. And then to toggle things, we usually use the XOR. So basically, the difference. What XOR does is if it's 0 and 1 together, then we have 1. If it's 0 and 0 together, something similar of the similar kind, or 1 and 1, it would be 0. That's the idea. If it's 1 and 1, it'd be 0 as well. So that's the idea. If it's 1 and 0, it's also 1. So that's the idea. If it's different, then it's 1. If it's same, then it's 0. That's what XOR does. Some other things here, guess, yeah, just being careful with the long. And then here is just some advanced hacks of like bitwise operators, which I'll talk about later. And then there are some built-in functions for C++. We can use built-in pop count, which returns the total number of ones in the binary numbers. So it's pretty nice. There's other kind of functions that we can use CLZ, counting leading 0, CTZ, counting trailing 0, parity, which basically counts, which is pretty nice. We have a lot of these functions. I think the one that gets used the most out of this is definitely the built-in pop count. And then these were some of the notes that I kept for myself. I think I don't necessarily need to go over it right now because I'm going to go over my own notes, which I think makes a bit more sense and is more comprehensive. So in the bitwise, we kind of have a lot of different scenarios of things that are kind of useful tricks to know or things to be aware of. So the first thing is, and all of these tricks kind of are definitely doable if we were to kind of implement it using other kind of operators or logic. But bitwise is more efficient and faster, I'd say. So it's definitely nice to know these tricks to save time. So for instance, when we're trying to check if it's odd or even, we usually do x mod 2 equals 0, right? Um, Obviously, the modulo operation is not very efficient. So what we can do instead is we can just check the least significant, um, the last digit, I meant. This is written wrong. It should be the last digit. Like, if the last digit of this thing is 1, then it's odd. If it's 0, then it's even. Because if we were to think about something in binary, right, it would just be, if we were to write it out, it would look something like this. The last digit would be 1, the next one would be 2, the next one would be 4, the next one would be 8. All of these are powers of 2. So then everything on the left-hand side over here would be all powers of 2, so it's definitely even. And the only thing that determines parity is the last digit. Um, Basically, then that means that if we do x and 1, if it was odd, then it would be true. Then if it's even, then it would be false. So that's the idea behind it. So simply we can just check with x and 1. Yeah, that was a mistake I wrote over here. It should just be the last digit, um, the rightmost digit, like the rightmost. And the second one, that kind of nice property is if we want to see if a number is a power of 2. If you kind of want to do like divide by 2, and then modulo, see if that is not efficient, right? So instead, we can just kind of think about it again in binary. If something was a power of 2, then it must have meant that in this long sequence of this, there is exactly one digit that is 1, and every other digit is 0, right? Because anything in this representation is to the 0, to the 1, to the 2, to the 3. So as long as you have exactly one of it, that would be a power of 2. And that's the only way for that. So what we can do is if we were to do x minus 1, then that specific digit becomes 0, right? And everything to the right of it would become all ones. So then what we can do is if we were to AND the two, then it would have meant that it would be 0. But otherwise, if it wasn't if it had any other things that was if it had more than one ones, then it would have meant that it would have been there would be at least a one somewhere in this number, so then it would be greater than zero. But the exception for this is that it doesn't work for x equal to zero. So we just have to write this condition as x and x minus one. And then we have this and condition just to make sure that in the case that x is zero, then that's not true, right? Because it doesn't make sense if zero is a power of two. So that's just kind of an extra condition we want to be aware of. So the third thing that kind of nice property we should know about is kind of checking what the kth bit is, right? So if we want to check if the kth bit is set, then we can just think of the kth bit as basically one shifted left k times, right? So that would be 2 to the k. So essentially, if our x was just a random number like this, and then we were to shift like this thing to exactly that, and then we were to check with the and thing. If this was already 1, then it would be 1. If this was 0, then it would turn to 0. So the way we can check is just x and then we just shift this 1 over by k, right? And then if we want to toggle the kth bit, what I mean by toggle is if it was 0, I change it to 1. If it was 1, I change it back to 0. Then what I can think about is I definitely have to shift it to this again, right? That's just unnegotiable. And then what I can do is I just do this XOR sign where if it was the same, then I just change it. If it wasn't, then I just change it back, right? So then that makes sure that I get what I need, the toggle effect. And if it was to set the bit to 1, then I would just do a OR, right? Because if it was already 1, then ORing it with a 1 doesn't change it. And if it was 0 with OR with 1, it would be 1. So I just do that as an OR sign. And if I want to unset the kth bit to 0, then I first take what I have over here. Then I negate that thing. Because if I want to change this, I have to definitely get a 0 at that spot, right? So the best way I can do that is just to negate that. And that I would want to end it so that I don't change anything that was the same before. So I keep all the ones because all the ones would still stay the same if it was paired. The zeros would remain as 0 up here. So the ones actually don't create any impact on what the original number is. And I ensure that the bit that I'm caring about gets turned to 0. So that's why I do x and then the negation of x shifted left by k. The fourth property that I kind of found pretty interesting was I already talked about this, was just basically multiply divided by 2 to the k. So left shift is just multiply, and then the right shift is just divide, which rounds down. This is pretty used quite commonly. Fifth property we have if you want to find x modulo 2 to the k, right? Um, a nice way to do this is x and 1 shift left shifted by k minus 1. Why does this exactly work? We can kind of think of it this way. Let's suppose that x was just a random number, let's say, and then we have a number like 2 to the k. 2 to the k is just basically a number with k bits, right? And then with the first bit of it, that as 1. So if we were to do that number minus 1, then the first digit would be 0 and everything that follows would be all ones. So if we were to kind of um, end this number with x, then we would just basically get the last k minus 1 digits, right? And if we were to get the last k minus 1 digits, then that's essentially what our remainder is by definition, right? Because this is in binary, so then we're just dividing it by this number. So this would be divisible, this would be the remainder. Pretty straightforward, let's say. Sixth property, um, it's basically when we swap two variables without a temporary variable. So what we usually do is if we want to change x and y, we would set x equals a temp. Um, like basically we would first, I meant like basically I should write this. So if we want to swap x and y, then we would have to first define TMP to be equal to x. Then we're gonna set x to be y, then y to be TMP, temporary. So that's kind of how we exchange X and Y values. But what if we have to do this many, many times and we don't want to store such a variable TMP, right? What's kind of a way around that? So something we can do is X equals X XOR Y. Y equals X XOR Y, and now X is equal to X XOR Y. Why does this exactly work? Because if we were to write it out, then the first step would have set X to be equal to X XOR Y. And then the next step would bring y to be this. But if we were to XOR y with itself, then it would have been just x, right? Because if everything with y would have been just um y, then this thing would have just been all zeros. So all zeros with x would just be the ones would just be preserved, which would just be x. So then if we were to bring this back to this, then x would have been this. But then we know that we have x and x, so then that's just basically y. So then we have our y. So then we successfully change x to y and y to x. So it's a pretty neat way trick. And then the seventh property we have, basically if we set x to be one value and then x to be another value. So basically the idea behind this is that we have a value of x. And then we just want to swap whatever value it is. Let's say that if x was equal to b, then we want it to be now a. And then if x was previously a, now we want it to be b. So like for instance, if it was previously 5, then we want to set x to be 10. Otherwise, if x was 10, then we want to set it to be 5. So like we just want to kind of switch x to be the other value. So then what we can do is we can set it to be 10 XOR 5 XOR x. So what that does is whatever the x value was originally, using the same trick as 6, we would have the x and that exact same value would cancel out, leaving the other value, right? So that's the same idea. And the 8 and 9 properties are basically the same, a plus b, but just counting it differently. So what a plus b does is suppose we have just two numbers, right? And we can count the things in two ways. For instance, if we were to draw the Venn diagram and we have a and we have b. If the digits were this, like we can count it in two ways, right? A plus B would just be this section of A plus this section of B. We can count it as the difference, which would be, let's destroy. Like, let's say the difference would have been this region. The difference would have been whatever was in A and whatever was in B. So it would have been looking something like this. This would have been the difference, A XOR B. And then we know that there is a region of similarity, which is here, right? We want to make sure that because we want to do A plus B, this region is counted twice, so that's why we have 2 over here for this. So that's how we get A plus B is just equal to the difference plus 2 times the overlapping region. Obviously, there's another way to count this. If we want to just do this in probability, we have learned that if we were to do this, we can first count the union, which would just be this entire region right here, right? It's just going to be this region, the entire region. So the union of this, because OR just takes the union. And then next what we have is because this region is overlapped twice, right? We need to count it a second time. So how we're gonna get counted a second time is if we were just to take this region and add it another time, right? So we get exactly the same sum, but what we end up doing is that here we just count this whole thing as 1 and then we add this back once. But it's the same way, so it's pretty nice. And then the 10th property is basically finding number of set bits in X in O1. Because usually if we were to do it ourselves, it would be much more complex. I say, I'm not sure how exactly they implemented this in O1, but it's pretty neat. They got it to the pop count function that I told about that was built in could have been is O1 and kind of time complexity. So that's kind of a neat trick that I talked about earlier that's useful to use. And then next I kind of went into kind of some other useful operations like finding all subsets in increasing order because we're kind of always interested in that. So some things that we can do for this is basically do this kind of algo. B equals B minus X and X, where our X was just our, like basically our set, and then our B is the subset. And then we started off at B equals 0, right? Because we picked nothing. That's always like the minimum subset. And then we find an increasing order. So we can do with this is essentially how this algo works is that let's say our x was this number. This first number is just going to be indicating the sign, right? So then our x is this number, our b is just all zeros. What we can do is x minus b. X minus b is essentially all the items that are not used are indicated by the ones. That's what x minus b represents, right? And what we want is now we want to take the negation of that. So then the negation of that would just be b minus x, right? And by taking the negation, what this means is basically using the two's complement. So we're just going to isolate the least significant bit and then leaving, if we're going to isolate it, that significant bit is just one, right? And then everything to the left of it would be flipped and everything to the right of it would be equal to 0. So then what that leaves us is, let's say here over here, we see that, okay, this is our least significant bit, right? Because it's the it's the rightmost digit that's 1. So then everything on the left, like the right-hand side is equal to 0. Everything on the left-hand side has been flipped from the state. So then what that means is that we honestly don't care about what the left-hand side is, right? Doesn't matter to us. So we're just going to basically clean it up with the x. So we're going to do and x with that so that we could get rid of it. Because we were flipped and then now we flip back. So then if we were to do and, everything over here would have been turned to 0. And then this is the digit that we're concerned with that we want to kind of preserve, right? So this would have been preserved because both in the state and the state we have this. And then whatever is whatever over here. So that makes sure that we can always find all the subsets in the exact increasing order. And descending subset is basically using the exact same logic. So our kind of equation would just be b equals b minus 1 and x. So what that does is we just subtract 1 first, and that basically flips the least significant bit from 1 to 0, right? Because if we're subtracting 1, we need to take the digit that is on the most that is the closest, and that is the least significant bit. So that changes to 0. So then the right hand side will all be ones. So then we can do and x, and then we can just take away the extra garbage values from it. So that's the idea behind it. And then the final last kind of useful kind of property is finding lowest set bit. So what we can do is we can just do x and the negation of x. So it's the same idea of using the two's complement property, because what the two's complement does is it leaves the least significant bit alone as the 1 value. And then the right-hand side would all be 0, the left-hand side all flipped. So when we end that with x, the right-hand side, because we know that's all 0, no matter what it's end with, it's all going to be 0. And then we know that the left-hand side is flipped, so we're always going to get the 0, 1 combo. And if it's a 0, 1 combo, it's going to be 0. And then only the least significant bit is preserved in the line, so it's kept as 1. So that's how we get the lowest significant bit. Okay, cool. That ends off this kind of chapter that introduces kind of C++ concepts in general.